Hey there! We are starting chapter 3 now. We're going to start looking at the properties, the material properties of materials, and how different materials behave differently under stress. You can think about if you had a rubber band and you applied a force, just a 10-pound force, whatever, on a rubber band, you're going to be able to see that stretch. Now, if you take a paper clip of the same diameter as the rubber band and it's made out of a different material and you put 10 pounds on it, it's going to have the same stress, force over cross-sectional property if we have the same diameter, but it's going to have a different strain. So the relationship between load applied and the deformation is a function of that material. Okay, so let's just again, I know. What does normal mean? It just means perpendicular to the cross section, okay? Perpendicular, it's a push, it's a pull. We have a normal force, we have a normal strain, okay? And then we had shear, okay? We had that shear, but today we're going to just talk about normal. So we have this relationship between stress, which is force over area, and strain, change in length over length, okay? So how can we discover all these properties? Okay, how do I know mathematically that the rubber band is going to stretch more than the paper clip as two different materials? Well, we can do what's called a tension test. And if you have taken material science or possibly the strengths lab, you may have already done some of these tests like this. But in labs, following standards, we can pull specimen apart after apart after apart after apart, measure the stress, the load coming in with a load cell, measure the strain, the deformation, and we can get material properties, which we can go to a book and look up. Okay, so the setup's going to be something like this, and materials are going to respond uniquely to the given load, and so we put in a force, we can measure the elongation, and we can now plot that load deformation, okay? So when we do that, we have grips that hold onto the specimen. We have an extensometer, which can measure the elongation. So we might have the gauge length, that's our original length, okay, kind of like in the middle of the bar. And as we pull it, that gauge length is going to be measured and we can see that increase, okay? And then we can plot our load deformation, okay, our load deformation. And we're going to find that we have kind of this really nice straight region for most materials, and then we kind of go flat, and then we kind of go up a little bit, and then it's over. Okay, so we're going to talk about all of those pieces of the graph because there's specific material behavior being exhibited. Okay. So before the test, we're going to note the cross-sectional properties, okay? The gauge length is going to be recorded, the area is going to be recorded. During the test, we're going to be able to record the amount of load, the amount of force that's being put into that system, that tension that's being put into that system, and that's going to be recorded. And we're going to be able to measure the elongation with the extensometer, and we have lots of information, okay? So at the end, we are going to load that until the material fails. And if you think about a bar that's perfectly round, that doesn't have that kind of necking as this figure shows, it's going to start off with, perfectly round. It's going to have the same cross-sectional area. And as we're pulling, we're going to have an area where we start to decrease. Okay, so as things get longer, what happens to their cross-section? As they get longer, the cross-section has to decrease, and it's not a constant from top to bottom. Okay, it's not going to everywhere automatically decrease the same cross section. Okay, and then it's going to completely come apart. So we will measure the final gauge length so we can see everything. We can measure the final diameter, and we can calculate the strain, because strain is just change in length over length. Okay, so we are going to have, now these are very important. You may need to watch this 12 times. You may need to read your book. You may need to make flashcards because these are vocabulary words you're going to hear over and over beyond this class. So the first thing is we have the elastic region. The elastic region is where you can load something and unload it, and it goes right back to the original shape. Load, unload, right back to the original shape. Load, unload, back to the original shape. It is a linear relationship between I'm applying a force, I'm getting a deformation, okay, and it goes back. I'm applying a force, it's going to be the identical deformation, and it's going back. It's elastic behavior. Think about it like a rubber, an elastic, right? This is kind of an elastic. The deformation is linear to the load that's being applied, okay? And that is, you know, where a lot of our design is going to take place. We don't want to have like permanent damage, if you will. You know, we want things to be loaded and unloaded and go back to the original design in terms of dimensions and lengths and behavior, material properties, etc. Okay, so it's loaded and unloaded just like new. When we move out of the elastic region, we move into the plastic region, and I can unload it, okay? But it's not going to go back to the original length. There's going to be a little bit of plastic deformation. It's going to have a permanent change in length, okay? So we can still load it and unload it, and we're going to find that it loads and unloads parallel to that elastic region. But now when we unload it, it has a different length, okay? It has a different length. And that's an important concept. So when we look at sections 2 and 3, we can see that as we load and unload, we are following a parallel behavior to the elastic region, but it's not coming back and down, up and down at the very same, I guess, original and final lengths like you find in the elastic region. There's that permanent set. The other thing I want you to notice is if we look at our load, if we look at the y-axis, which is our load, you can see that it's barely increasing in load, but we're getting lots and lots of deformation. So we kind of like apply this tensile force until we get to kind of a certain point, the end of the elastic region, before we move to permanent deformation. And now I don't have to apply load anymore. I can kind of almost keep that load constant, but deformation is occurring. And I want you to think about silly putty, because silly putty is one of those materials that's pretty easy to see. I want you to think back to your childhood and stretching the silly putty. And it's kind of stiff at first, and then you kind of get to a certain point, and then it's just like stretching and you're not doing anything. It's yielding, okay? Yielding is we're not applying a whole lot of force, but we're getting lots of deformation. So we go from a line like this to a much flatter line, okay? We are no longer elastic. Even if I unloaded at that number 3, it's going to unload, it's going to come parallel down, back parallel to my that elastic line, but it's going to have a permanent strain. It's got a change in length, right? It's got a built-in strain now because we aren't going back to our length final does not equal our length initial like it does in the elastic region. So in the elastic region, when I unload, I go back to 0 strain. Length final equals length initial, so LF minus L naught is 0. When we enter yielding, which is the plastic, we're in that plastic part of our region now, the length final after I unload it is a different length than what I started. So there's a permanent strain. Okay, so that point where we go from elastic behavior, I can load and unload, load and unload, load and unload. There's no residual strain. It always goes back to the original length. That's my sigma y. That's our yield stress. When you go and look at a chart and you look at material properties, the yield stress is super important because that's the end of our elastic relationship. Okay, that's the end. After we go past that point, when I unload, when I take the force off the specimen, it will not go back to its original length. There is permanent strain set in, okay? That's just super important to understand. So when we reach the strain hardening, that's kind of there over there where number 4 is, we kind of reach the strain hardening where the stretching is becoming very obvious to our eyes. If you think back to that silly putty when you were a kid and you could kind of stretch it and it, you know, you're not putting a whole lot of force and then all of a sudden it's like, I mean, I just remember like gooping out, like it just totally was stretching apart. it's obvious. Okay, it's obvious. You can see with your eyes that there's a change in that cross-sectional area. Okay, and we reach the ultimate load. So that's up there at 4. So when we say stress ultimate, okay, stress U, that's the ultimate stress that we can handle. Okay, it's above yielding. Okay, it's in the plastic area. And it is the ultimate stress we can handle. And we kind of hit that, and then whoop, usually you can just see the load just almost going away and fracture occurs. Okay, so then we have a stress at fracture, which is beyond and lower than that ultimate. Okay, so that's where we have that necking is occurring, where we can start seeing that there is elongation of the specimen. You can tell it's not going to go back to the original shape. You can start to see a very significant decrease in that cross-sectional area. The load decreases, and then boom, fracture. Okay, so that's our fracture stress. Okay, so important things you all have to understand. When we have our stress equations and we look at stress-strain relationship, the equations are very dependent that we're in the elastic region, okay? If I apply 10 pounds to whatever my cross-section is of my rubber band and then I unload it, it is going to go back. It is going to follow that elastic slope of the line. I can load it, unload it, load it, unload it, load it, unload it. There's no residual strain upon unloading. That length final, after I unload it, goes back to the original length. So we have to understand you're going to have to start making sure that you always check, am I within the elastic limits of my material, or have I gone over? Okay, where you have permanent deformation. The plastic region, you have permanent deformation, you have permanent strain. You will never go back to the original length. When you unload, it will be slightly longer. It will be slightly longer than what you started. It's not going to go back. It's plastic deformation. Okay, it has permanent strain built in. We could even calculate how long is it permanently. Okay, do you see why you wouldn't always want to design in that area? Especially if you have tolerances, very tight tolerances on lengths of things to work together as a unit. It could cause issues. Okay, so when we look at a stress strain diagram on the left side over there, we have our stress. And what is stress? It's that force over a cross-sectional area. On the bottom, we have strain, and we have very distinct parts of the graph. First, it's divided into two: elastic region, plastic region. Okay, then the plastic region is divided into yielding and strain hardening and that ultimate strength. And so it has its own set of divisions, if you will. Okay, and materials are going to have a different slope in that elastic region. They're going to have a different amount of deformation that takes place well in the yielding. Okay, depending on if they're a ductile behavior, if they are a brittle material, all sorts of things. It's kind of cool. Okay, so for this low carbon steel and this aluminum alloy, we can see they each have a specific yield stress. They each have a specific point where we go from elastic behavior to we are yielding, and we're going to have some sort of permanent deformation even after unloading. Okay, they both have their own unique ultimate stresses, and they both have their unique fractures. So it's just important. So the proportional limit is that stress strain plot where we no longer have that linear behavior, that as I apply load, there is a nice relationship with how much deformation takes place. Okay, I could, if in the elastic region, if I tell you this is how much force I'm putting in, as long as I'm in that elastic region, I can say this is how much strain I have in my system. Okay, and so we can use that proportional limit is where that behavior changes. So our next vocabulary word is modulus of elasticity. And many of you may have heard, what is the modulus of elasticity? Okay, you may see it written as MOE in a table, because sometimes tables don't have a lot of room. It is literally the slope of the line. It is that linear relationship in the elastic region of stress and strain. Okay, super easy peasy. How do I find it? It's the slope of the line because it's a straight line, right? It's a linear line. Rise over run, stress over strain. I can draw over from the stress, draw down and pick out that strain, divide the stress by strain, and voila, as long as I'm in the elastic region. So when I tell you what the modulus of elasticity is, remember that's the slope of the line in the elastic region. It's just rise over run, it's change in stress over change in strain. It's called Young's modulus. So you might see it as Young's modulus, MOE, modulus of elasticity, elastic modulus. They are all the same words for the same concept. Okay, it's the slope of the line. In this case, the slope would be if we went up to 43.5 and then we came over to 0.041, the modulus of elasticity is 10,610 KSI. So because our units are stress in KSI and strain, which is unitless, even though we kind of put like inch per inch on there, our units on our modulus is KSI. It's the same units that we have for stress, okay? So we come up with this fancy equation. If I say that E, which is the slope, is stress over strain, I can multiply through by strain, and I get stress equals E times strain. Stress, P over A, that internal normal force over A, equals Young's modulus strain, change in length over length. So now I have a way to look at this relationship, and if I know the force and I know the cross-sectional area and I can find the stress, I can now tell you how much change in length you have. So when we did the strain chapter, we just told you it rotates 2 degrees. Its change in length is this much. Its strain is this much. Now we could do all the same problems, but we could make them statics problems where you have to find the force in the cable. And once you find the force in the cable, then you can use Young's modulus of elasticity to find the deformation. Stress equals E times strain in the elastic region. In the elastic region. Once we leave that, you can see it's now like this curve. The blue line is a curve. It's going that way. It's not the same relationship. Elastic modulus of elasticity. Okay. And so then as we move into that inelastic strain, it's inelastic. We're going to have permanent strain. As I load and unload, you can see that as we load it and unload it, there's going to be, we're not following the same path to come back up to loading because we have that permanent strain now. We're going to have a permanent change in length. Okay. And so that proportional limit, again, is where we change from elastic behavior to plastic. Okay, elastic length recovery, cross-sectional recovery. It's just like new, just like new. When you move into that plastic, that inelastic strain, you have a permanent set. You have a permanent deformation, a permanent change in length. Okay, so most engineered components are designed to function elastically. Okay, because we want to avoid that permanent deformation, that permanent change in length. So our size and shape, okay, is not, it's significantly not changed. It's small strains, it's small changes, okay? There are sometimes, however, cases where in a building, for instance, we may have components that are designed to fail. They are designed to reach that yielding, and then you saw it can absorb so much energy as we're having deformation before we kind of increase that load again. If we have an earthquake, we don't want catastrophic, right? We want members, maybe members that are designed to fail so that we have time to get people out of the building and potentially not damage the entire rest of the building. So it's not that we don't always design an elastic. We might, but there are times that we might not, okay? So anyways, it's just loading and unloading and unloading and unloading. And to find that elastic limit, that where do we stop? You load and unload. You load and unload. You load and unload. You load and unload. All of a sudden you're going to load and unload, and when you come back down, it does not end up at zero strain. It ends up with that permanent set. And that's the point. You found that point of elastic limit. Okay? So for many materials, it's kind of hard to figure out where the elastic limit and the proportional limit ends. And so they have methods for coming out on with a 0.02% offset method, where we're not going to go into that. You go into that in your other classes. You can read through this. Okay, you can read through this. The important thing is that we have this proportional limit. That's where the actual line is no longer proportional when you're adding stress to strain. We've reached the yield strength where we're changing our behavior. Okay, so we can talk about engineering stress and true stress. When you're testing and you have an original cross-section, a cross-sectional area, what happens as you start to really stretch that bar? What happens to your cross-sectional area? It starts to get smaller. So really, if stress is load over area, right, load over area, you're going to have lots of changes as we start. Your stress is going to change not just because of loading, but because of cross-sectional area. So when we look at true stress, that is absolutely coming through and following the change in the cross-sectional area, versus engineering stress, where we just assume it's the original area and we calculate our stress based on just the original area and not constantly changing the area. Okay, so that's the engineering stress. It doesn't take into account that decrease in the cross-sectional area. We just say, oh, the original is 2 inches squared. That's what we're going to use for all of our loads over areas. The true strain, the true stress takes that into account. We measure the change in cross-section as well, but don't worry about that. So ductility. Ductility is the amount of strain. What is strain? It's that change in length per length that a material can withstand before fracturing. So if it's a very brittle material like concrete, we're pretty much hitting that elastic region, and then poof, we're going to have that concrete in compression, or that concrete in tension is just, it's done, right? Now, if we have something like a rubber band, it might be a little bit more ductile. Actually, this is not going to be as much as like steel. With steel, you can see that it stretches, and then it's just kind of stretches, and then you can see there's permanent deformation. So we have this long range of ductility where we have like that stretch. Now, the stress strain curve, it's absorption of energy. Okay, so if you think about the area under the curve is how much energy it can absorb until fracture. A ductile material might be really useful in an earthquake situation where you need energy absorbed, energy absorbed, energy absorbed, so we don't have a catastrophic failure of the whole building. Okay, so ductility is important. Okay, when you look at the failure of a tensile specimen, you're going to find if it's ductile, we have this nice cup and cone type failure. And again, if you've had material science or you're taking the strengths lab, you may have already seen all of this. Okay, so we could have different steels and they could have different yield stresses. Okay, they could have different behaviors in terms of ductility after yielding, and different behaviors once we reach that ultimate. Okay, so it's important to understand what material you're using, so when you go to a book or a table, you know which numbers for material properties you need to pull, because not all steels are the same, not all aluminums are the same. Okay, not all pieces of wood are the same. If it's a maple is going to behave differently than oak. And so you have to always, when you're designing, make sure that you're understanding your material properties. Okay, so modulus of resilience, we talked about that energy under the curve. Modulus of resilience is the ability of the material to absorb energy without permanent damage. I think of a rubber band as resilient. This rubber band, oh, I just broke it. Eek, forget that I broke it. It's resilient. Stretch, 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 back to normal. Stretch, stretch, stretch. Look how resilient we are. Okay, so when modulus of resilience, it's that area underneath the stress strain curve in the elastic region. Resilience. Okay, resilience. It's okay. So if our modulus of elasticity, this line, is a linear relationship, then I don't need a fancy formula, right? What's the area of a triangle? 1/2 base times height. 1/2 base times height. 1/2 base times height. Easy peasy. Okay. Or you can have a fancy relationship that says sigma and strain, and you kind of be like, what? Just, it's the area under the curve. Pretty easy. Okay. Modulus of toughness. This is the strain energy at fracture. This is all of the energy that can be absorbed before failure occurs. So it is not, is it just the elastic region, but it's all the entire region of the graph. It's the entire area under the curve. That is your modulus of toughness, because you are only so tough, like you are only so tough until you are not tough enough. Okay. If you are a weightlifter, you might be able to lift 300 pounds, but you add 5 more pounds to that, you're not lifting it up. You're only so tough. Okay. You're still tougher than me, but you're still only so tough. Resilience. Resilience. I'm resilient. I can come back and come back and come back and come back. That's my elastic region. Toughness. The entire area under the curve. I can only give so much. Okay. So it's just that ability to absorb and dissipate energy. That's really what's happening. When you look at books, this is out of a different book, and that's where you have to understand what brass am I working with? What iron? What steel? What steel am I working with? Because you can see, okay, the steel has the same specific weight, but as we go through, the modulus of elasticity is slightly different. Okay, its shear modulus is different. We'll talk about shear in the next video. Its yield strength is slightly different. Its ultimate strength is slightly different. So you have to have this understanding of, what do all these numbers mean? What is yield strength? What is ultimate? What is the modulus of elasticity? What is shear? You have to understand what you're pulling off the chart. You also have to understand very much what material you're using, because it's going to significantly alter the capacity of your system, right? If you're trying to design for a system and you think that you've got like this yield strength of 82 and you're using the structural steel, A36 steel, you only have a yield strength of 36, you're in trouble. You're in huge trouble. We do a lot of problems in here with A36 steel. A36 KSI is the yield stress of A36 structural steel. It's pretty easy. It's pretty easy to remember. But you have a chart like this in the back of your Tech e-text. And I think I have one in your homework module that you can just print out so that you can have it on hand. But please do not send me an email and say the problem statement didn't tell me values for my material. Pull out your book, Google it, okay? Find a chart. Okay, they're published. Anyways, we're going to do some examples, and then we're going to have another video on shear, the shear properties, and how shear stress, shear strain, and elastic, normal strain, normal stress are related. Okay. Again, you may want to rewatch this. You may want to take notes. You may want to read in your book, because this stuff is super, super important, and it is a lot of definitions. And you have to be able to understand, if I say to you, you need to use the yield stress or the yield strength, or what is the modulus of resilience, you have to know what that is. Okay? See you in a little bit.